Android, but Vulkan is going to be the primary API if you want to get to your GPU on Android systems, starting with Android N. The other big difference, and hopefully the value of a cross-platform open standard to the industry, both to the software developers and the silicon vendors, is just like OpenGL. Vulkan is extensible. So if Vulkan doesn't have quite what you want today to meet your market needs, you can always build an extension. You don't have to ask anyone's permission. You can do whatever you want, extend it however you need. So that's the way that people can ship innovations into the market at their own pace. If a GPU vendor has a new functionality, we can do a Vulkan extension and expose it today. We don't have to wait for the platform vendors to want to also ship that functionality. So, as always, we feel that open standards play a really important role in enabling the 3D industry. So, what are the pros and cons of this explicit control? What does it mean to a developer? Essentially, what it means is that the driver is going to be told what to do, and for efficiency, we want to be told what we're going to do ahead of time. That means we don't have to stop in the middle of rendering a frame and say, okay, what is it you want me to do again? We want to have all the information we need up front. So the programmer tends to have to provide a lot of information up front. But once things start to run, things will run very efficiently and with low latency. And it will do it without any surprises. It will just do what you ask it to. There's no magic in the driver, well there is some, but much less magic in the driver than there was with OpenGL. So you might have heard that if you're new to Vulkan, there's like a lot of hundreds of lines of code you have to write to kind of get your first triangle on the screen. That is true, but it's relatively straightforward once you have gone through it, and there's lots of open source examples now. Involved in the Vulkan working group. And the big difference too, from an ecosystem point of view, is OpenGL was largely designed by the silicon guys sitting around the table, bringing second-hand experience from the developer community as to what people wanted. Vulkan was very different in a really healthy way. The key ISVs, primarily the games engine vendors, actually joined and came into the working group as we were doing the design. And so we didn't have to guess anymore. We were being told in often point-blank terms what it is that Vulkan needed to do. And that radically changed how the API was designed in a very good way. So we really welcome the input from people like Valve and Unity and Epic, Blizzard and EA, or the rest of the developer community that really helped us create Vulkan. Vulkan was done in 18 months, and when we launched it, because OpenGL will kind of dribble out, we do a spec, and then we have performance tests, and then we have some documentation, and then applications would ship. With Vulkan, everything, hard launch, everything launched at the same time. The spec, the drivers, the tests, even applications that we're using the API, because those application vendors were inside the working group, seeing what was happening in real time. So which developers should use Vulkan? We're trying to be very upfront and straightforward, and saying that there are pros and cons. There's all those advantages that we just went through with Vulkan, but there are disadvantages. It's more verbose code. You do need to understand the GPU pipeline more. You need to understand when the buffers are going to be needed, when should you allocate them. And for some people, that's too much detail. Just let me stick with OpenGL and OpenGLES, let me use your hundreds of millions of lines of optimized code, thank you very much. And that's fine, particularly if your application is not CPU limited. You won't get any advantage from the multi-threading, for example. You may not get any speed up at all from going from OpenGLES to Vulkan. If you're GPU limited on OpenGLES, you will probably remain GPU limited on Vulkan. Vulkan doesn't make the GPU go any faster. We're just feeding work into it in a more efficient and effective way. So, if your app is CPU bound and you can multi-thread it, if you want to really enjoy the low latency, no surprise, no hitching, but in virtual reality, for example. Of course, if you hitch, you can really disrupt the application. Then Vulkan can add a lot of value to you. But if you're perfectly happy on OpenGL and OpenGLES, you don't need to move, because those APIs are not going to go anywhere for at least another 20 years. So Vulkan is low level, and we're kind of watching with interest to see how the ecosystem evolves. It's still not even a year since Vulkan launched. We're still in the very early days. So course applications can use Vulkan directly. But just like OpenCL, most people perhaps will get benefit from Vulkan without actually having to write a single line of Vulkan code, because the games engine that they use will be highly optimized for Vulkan, and you just use the games engine in its new version, and you get all of that for free. And we have an increasing number of games engines that are being ported over Vulkan, all your favorites. There's this interesting space in the middle, which we're really interested to see how this evolves. I think there's a space, just like OpenCL has lots of middleware that runs over the low-level API. Some of those libraries make it easier, some make it easier to port from OpenGL, some domain-specific libraries that can really benefit from having the Vulkan low-level acceleration underneath. I think this is going to be a very active area for the community, hopefully the open source community, as well as Khronos. And this is a very similar ecosystem shape as WebGL. We'll get to WebGL later, but WebGL is a browser API, is OpenGLES in JavaScript, and OpenGL and OldStarDX. In the mobile space, Android, with the Daydream initiative, heavily investing in virtual reality. The Daydream stack is the virtual reality functionality over Unity and Unreal, and both of those will be accelerated by Vulkan on the Android platform. So, can you run Vulkan on Apple? Is probably the most asked question. Apple have not expressed any desire to ship Vulkan at this point, but there is a third-party library vendor, Brentwood Workshop, that's now shipping Molten VK, which is an implementation of Vulkan that runs over Metal. And this was a demo at Siggraph. This is the Android Vulkan demo running on an iPad. And it's been an interesting experience. And the good news is that the overlap is actually quite high. Brenwell saying that it's over 80% of the Vulkan API is easily transported down into Metal, and so you can get good performance because it's straight one-to-one mapping. There's not overhead. So this kind of bodes well, I think, to being able to create a portability API that spans the three lower-level APIs. So, but if you're interested to use Vulkan on Apple, then the link is there for you to try. If you want, in general, to get to Vulkan developer resources, of course, the links you need to start with if you're looking to start looking at Vulkan development. I mentioned that everything, well, the performance tests are open source. Actually, the spec is open source. Everything to do with Vulkan is open source and on GitHub. We're definitely trying to be more transparent and open with the community with this new generation of API. Everything is licensed under Apache 2, so we encourage everyone to get involved. There's quite a few active repositories there, ports, tools, tutorials, so please do get involved and see what's there. We're trying to build this Vulkan community where we're doing this together rather than Khronos trying to hand down tablets of stone to the rest of the community. And if you're using Vulkan, let us know, because we're actually interested to promote people using demos, applications, engines. Let us know. That's the Vulkan working group. We have reference cards, and people that came in late, there's a big pile of reference cards here, which you can come grab anytime after. Please take more than one. I don't want to carry them home. So there's Vulkan and WebGL, so help yourselves to those. Okay, before we get off 3D, just want to mention OpenGL SC. This is the safety critical version of OpenGL. For those of you who have worked in safety critical domains like avionics, you know that the complete system has to be safety certified, which basically comes down to the design methodology and the testing methodology being documented, and then that documentation being documented, and everything being documented. And it's very expensive. Every line of code in a certified system can cost $10,000. So you know how much memory is going to be used before you start can really help, particularly in real-time type of applications. You can do compiler type techniques. You can take quite a complex graph and begin to collapse some of the nodes down into a sort of larger graph, which is what compilers do all day, every day. And data tiling, which is kind of a favorite of the GPU guys. We can avoid the memory round trip cycling by splitting the image up into cache-sized tiles and sending a tile down through the graph, one tile at a time, and that tile will just stay entirely in cache from beginning to end, so you get significant speed up. This is a graph from NVIDIA. This is not a performance benchmark against anyone else. This is just a snapshot of some internal experimentation we did. This is the same GPU. We had GPU accelerated OpenCV, which is not doing the one function at a time thing, and the green bars are the same GPU accelerated OpenVX. And if we took the care to put a graph that had a reasonable complexity, and we were doing mainly tile management optimizations here, if you're memory bandwidth limited, you could begin to get significant speed ups because of the graph optimization in the implementation. So this was kind of a confirmation of the concept that the graph is a useful way of expressing how we want things to run. So now we have, but still people get a little confused. Well, we have OpenCL and OpenVX. Now one is higher than the other, but of course in many cases people will use OpenCL or C++ or GPU, OpenGLES even, to implement their OpenVX nodes. But VX lets you get onto the hardware, which none of those programmable APIs let you do. So portability across different architectures. And Rada, standing in the back there, one of if you're starting with OpenVX, one of the best places to start is AMD has done an awesome implementation in open source, runs on OpenCL and x86 CPU, and their tool set there does a lot of graph optimizations for you. So you will look at your graph and optimize it, and has a lot of scripting capabilities, so for rapid prototyping, and just making sure that you're getting the best performance you can for your application using OpenVX. And everything's open source, right? Yep. So that would be my recommended place to start if you're wanting to look at OpenVX. So where is OpenVX shipping in production devices? The yellow blocks are the companies that are shipping OpenVX. These are all shipping OpenVX 1.0. The OpenVX 1.1 spec that provides more nodes, more Lego blocks, and better ways of clipping them together. That specification was released in May, just a few months ago, and the implementations will be coming soon. But just like every other Khronos standard, OpenVX is extensible. So the menu of nodes is quite small, particularly compared to OpenCV, which has thousands. But that's kind of deliberate because we want everyone to be able to implement all of it. So when you go to an OpenVX 1.0 or 1.1 implementation, you know what you're going to get. But of course, there may be some functions that are missing open for your application, but it's extensible, so you can always create the node that you need with your special source or with a piece of functionality that the standard doesn't yet support in core. Now I mentioned at the beginning the neural net extension. So your content is built using 3.js. But as again, as we were saying earlier, having this WebGL capability built into your browser is very flexible, and you can really build any type of engines or applications on top that you wish. So WebGL is based on OpenGLES. WebGL 1.0 is the version of the spec that's shipping today, and that was shipped in 2011, so it's 5 years. And the reason there's kind of a long pipeline here is that the underlying native API has to be pervasively available everywhere and debugged. And then the browser vendors can begin to use it to layer on top of. So there tends to be a few years delay. We're about to launch WebGL 2. It might just make it into 2016 or early 2017, which is based on OpenGL ES3. So that's going to bring a significant jump in 3D functionality for the WebGL community. How available is it? This is my favorite website for web functionality, caniuse.com. So if you plug in WebGL, it turns out that in the US, 95% of browsers, installed browsers now have WebGL, and globally, it's almost 90% of browsers. So it's all desktop and mobile shipping production drivers now support WebGL 1.0. A lot of tools I mentioned, 3.js, Babylon.js is from Microsoft, Unity 5, the latest build of Unity. You can now export to WebGL directly. Then there's a bunch of application-specific engines that will build over WebGL. A lot of WebGL applications out there, not just games, but companies like Autodesk are increasingly using WebGL for tools. So you can actually design your 3D assets and games in the browser, as well as deploy them in the browser too. Sketchfab is a company that lets you load a 3D object into your Facebook page, and that's all already working. So people say, well, I've not used WebGL, but you probably have, because Google Maps is a WebGL application. Every pixel in your Google Map, whether it's 2D or 3D, is using WebGL, which is where they get the high interactivity. And this has been one of the leading applications also that's really proven WebGL as a platform. So WebGL is great momentum. We have one piece though in the ecosystem for 3D across the network, and that is how do we actually get those 3D assets into a WebGL application? All the other major media types, audio, video, and images, they all have compressed and streaming media types, MP3s, H.264, no JPEGs. Now imagine the web if we didn't have JPEG, right? Every website used different formats of images. Well, that's exactly where we are right now with 3D, except GLTF comes to the rescue. So OpenGL transmission format. There's dozens of 3D file formats, so why is Khronos creating another one? There's no current format that is compact, fast to load, particularly on mobile devices, describes complete scenes. An OBJ file, for example, just describes a geometry mesh, is runtime neutral, it's not trying to force you to use those assets in any particular way, and is extensible. So GLTF is a JSON-based API. Use JSON to describe the node hierarchy, and then you have binary payloads for texture, for geometry, and shaders. And so you can create a complete scene, including with animations. And the GLTF 1.0 shipped about a year ago, and we're now just about to ship 1.1 that makes it much more testable and has simplified actually a lot of the spec, particularly around animations, so we have a validator. And the good news is that really at Siggraph, the other Siggraph in the summer, was where GLTF momentum kind of hit the launch pad. There's John Carmack saying that he needs this, he wants to support it at Oculus, and a bunch of other folks too, really getting behind GLTF. There's not a lot of rocket science. It's relatively straightforward. I bet a bunch of people here have implemented something very similar to this. The value of GLTF is that we can all agree on one way of doing it, and we get a tremendous ecosystem synergy. And that ecosystem is beginning to build. So we have a MIME type, so 3D on the web is GIMage. More streaming and compression, better efficiency, more animation. So the web graphics is though an interesting area. It's relatively new. There's lots of innovation going on, and Khronos is we're working hard to be a first-class citizen. So some of the things, people are interested to bring virtual reality into the web browser, which I think is awesome, because most virtual reality experiences, I think, end up being delivered through the web. And WebVR is built on top of WebGL, but the native APIs have lots of VR machinery built in. We were talking about bringing those into Vulkan earlier. Well, we need to bring those into WebGL. It's something we need to do. We had the whole portability problem. You know, we were talking earlier between Vulkan DX12 and Metal. Pokemon Go, of course, showing that the mobile people really want to use augmented reality, but the power of using the camera and compute is not there. Everyone was turning off the augmented reality in Pokemon Go to save their battery. So perhaps we need to begin to figure out how to bring OpenVX style vision processing into the web. Can we bring better general compute, the GPU, perhaps some JavaScript language extensions for general purpose compute? And the camera control API is going to be, I think, increasingly necessary as the phones begin to get depth sensors, multiple sensors. It's going to be increasingly difficult for the web stack to be able to cope with all of these different types of cameras. They need the help of the native API community to kind of figure out that fragmentation. So this is all in discussion, all very interesting. Love to hear your feedback on it. And finally, we made a new announcement here at Siggraph Asia, the Virtual Reality Initiative. This is so new, we don't even have a name, let alone a logo. And it's not a done deal. This is a call for participation. We're starting this, and we want people that are interested in virtual reality to get involved. So, what's the need for a virtual reality standard? So, on the left is where we are today. There's lots of cool SDKs, but they're all subtly different. There's the Vive, there's the Oculus, there's the mobile guys, the Daydream coming, Gear VR from Samsung today, OS VR, which is the open source. So applications and engines, they have to port to multiple APIs. And from the hardware vendor's point of view, it's also a problem too, because now you have to integrate your device into all of these different environments.